Okay, stats lovers, we are now in chapter 10, and we're looking at test of independence using what's called chi-square. So I know you're probably hoping to get a new distribution today, and we've got a new distribution. So just to quickly review the old distributions, we could say that so far we have studied a few probability distributions, including the binomial distribution, which was the first one we studied. And you know what they say, you never forget your first distribution. So that's the one you guys will remember forever, the binomial distribution. Then after that we studied the normal distribution. And of course the standard normal was a special case, right? Where the mean was 0 and the standard deviation was 1. And then we also studied student's t. So we have studied 3 distributions so far. And today we're going to study a new one called the chi-square distribution. And it's denoted chi-square. And we will use this distribution for hypothesis testing. So what we're going to do first is take a look at what this distribution looks like. So we need to go to the y1, go to your y equals menu. So to kind of review here, you go to the y equals menu. You just want everything to be cleared out. So you don't want any of your plots highlighted. So remember, if there's a plot highlighted, hit enter, go up to the plot, hit enter, and come back down and clear out all of these. So when you press y equals, you want it to look like this. And then we're going to just store these for y1, y2, and y3. So you get these from the distribution, right? It's just like before for normal CDF and all that. So you go second vars to get to distributions, and we want to do these one at a time. And then we want to get a picture of what they look like. So we'll put this one in, and then this one, and then this one. And depending on your software, when you go second vars and choose one of these, you may just see chi-square PDF with the open parenthesis, or you may see a couple of questions. So if you see the inputs, depending on your software, you may see this when you hit chi-square PDF, all this, or you may just see chi-square PDF open parenthesis. If you see the open parenthesis, just put x comma 4. Remember x, that's that button up in the upper left. It says x, t, theta, and n. You can just press that one. Now if you see this other menu, then what we need to input is put your x here and your 4 here, and then paste it on the home screen, or paste it on the y equals screen, and then you should see this. So another thing we're going to want to do is change the window in your calculator to match this window. So the x-axis, we want to go to your window and change the window from 0 to 20. Right? Go to the window button. It's up next to the y equals button, and make your x go from 0 to 20. And for the x scale, you probably go like, 1. X scale could just put 1, it'll put a tick mark every 1 unit. Or every 5, whatever you want to do. And then the y scale, we want to go from 0 to 0.25, and probably put a tick mark every 0.05. Okay, so once you do that, once you change your window, you should see this. And then if you hit graph, you should see this. So this is a chi-square with 4 degrees of freedom. And on your handout, we're going to want to draw this in there as good as you can. It's kind of hard to freehand this, but we need to see the difference between 4, 6, and 10 degrees of freedom. So try to sketch this on your handout in that open window there as good as you can. And then we just want to go back to y equals and try 6 degrees of freedom and 10 degrees of freedom for y2 and y3, and then we can see all of them at the same time. So when you're all done and they're all graphed on your calculator, you'll get a picture kind of like what I've shown. I've freehanded them, so they're not perfect. One thing that'll help you draw them, though, is the peak happens n-2. So 4 degrees of freedom, it peaks at 2. 6 degrees of freedom peaks at 4, and 10 degrees of freedom peaks at 8. So it'll help a little bit with the drawing, but they're not that easy to draw. But here's a question for you. What is the area underneath this first curve? It's 4 degrees of freedom. I know what you're thinking. 1. And you are right. What about the area underneath this curve with 6 degrees of freedom? 1. This curve with 10 degrees of freedom? 1. Always 1, right? These curves that we use with continuous functions are purposely created in that way so that the area under them is exactly 1 because we're using them to answer probability questions. Remember, all of these numbers on the number line are possible outcomes of some sort of experiment. So the sum of, and as we know, the sum of all the outcomes in the sample space has to be 1. So the area under these curves is always 1. So when you look at the chi-square distribution, you will notice that it is not symmetrical, right? Which way is it skewed? Remember, it's skewed where the tail is. It's skewed right. And like the student's t-distribution, it depends on the number of, what does the df stand for? Degrees of freedom. As degrees of freedom increase, the graph of the chi-square distribution becomes more symmetric, but it never gets totally symmetric. The mode or the high point of the chi-square distribution with n degrees of freedom occurs over n-2. Okay, so this test of independence, here's the thing about 10.1. We're going to go over this first. We're going to look at one example problem, and we'll do it by hand. And you're going to be rightly thinking, oh my God, there is so much arithmetic in here. This is computationally extremely intensive. It just would take so long to do even one problem by hand. And you are right. So this is one test where we'll do it by hand the first time. And then normally where I show you a shortcut and I say, but don't do this on the test or quiz. Or I'll say something like, just do this for checking. Well, in this particular case for test of independence, nobody does these by hand. It would take too long. So in this case, it's going to be really easy to do on the calculator. The calculator will do all the calculations for us. We just have to interpret the answer. But the problem that we do, we have to do it by hand the first time, and everybody does it by hand the first time, just so you see what's happening. Otherwise, you won't have any kind of intuition for it. So we'll do one problem by hand, and then I'll show you how to do it on the calculator, and then all the homework problems and all the test problems will be done on the calculator. Okay, like I said, nobody, unless they hate human beings, would not make you do these by hand more than, once or twice. So we'll just do it once. So here's our application. We're going to do a test of independence, and it is the independence that we've always been working with, right? Coin flips are independent of one another if the one event doesn't have any bearing on the probability of the other event. So it's the same kind of independence that we've been talking about before. So in this case, we've got a random sample of 160 patients at an HMO, a health maintenance organization, and we've got some information about their smoking status and blood cholesterol counts. So we're looking at two things. We're looking at smoking status and blood cholesterol counts, those two things. This information is organized in what's called a contingency table that lists the observed frequencies. So these are the actual frequencies, the one we actually saw, we observed them, right, or measured them. So we've got the observed frequencies in boxes called cells. So here's our contingency table, right? It's a contingency table. Got the observed frequencies, so 6. This 6 represents somebody with a low blood cholesterol count who's a heavy smoker. right? So this right here, this is smoking status right here. And these columns here are blood cholesterol count, low, moderate, or high. So the first thing, well, let me make a couple notes here. The size of the table is a 3x3. And the size comes from the number of rows, which are horizontal. So there's these 3 rows, smoking status. Number of vertical columns, there's 3 columns, blood cholesterol count. So this is a 3x3 table. So it's just the shaded areas that count for the size. So this is a 3x3 table. So the HMO would like to determine if there's any relationship between smoking status and blood cholesterol count. So we're looking for relationship between smoking status and blood cholesterol count. So in other words, the HMO would like to determine whether or not smoking status is independent of blood cholesterol count. They're going to use a 5% level of significance. Right, so we're checking for independence. Is there some sort of relationship between these two or not? So what we have to do first is just add up these columns and then add up these rows. And normally we would have you guys come up and do these on the whiteboard. But here, we'll just add them up real quickly. So go ahead and put those on your handout. And then we have this hypothesis. So we wanted to answer the question, right? The HMO would like to determine whether or not smoking status is independent of blood cholesterol count. So have this hypothesis, well, 2 hypotheses. And you notice you got this same notation, H sub 0 or H naught and H1. Or you could have H sub A if you wanted to, H sub 1 or H sub A. But now we have our hypotheses are listed in words, right? They're just listed in words. It's not like mu equals 7, mu is less than 7, right? It's still a hypothesis test, but this particular one listed in words. So we list the 2 things, right? What are we looking at here? Smoking status, blood cholesterol count, right? So in this section, every one of these in 10.1 can be listed this way. There's going to be 2 things we're looking at. We want to know, are they independent or not? And we always assume they are. We have to, because we're building our probabilities based on these being independent. So we're going to say, okay, let's assume that this is true, that H naught is true. Let's assume they are independent. And then we're going to use our chapter 4 and 5 formulas, mainly 4, to figure out probabilities based on these being independent. Right? So our null hypothesis is this thing and this thing, whatever they are. In this case, it's smoking status and blood cholesterol count. These 2 things are independent. The alternate hypothesis is that these 2 things are not independent. Okay? And we have the observed frequencies, which are the actual frequencies. So in other words, from our sample, we had our sample here of 160 patients, and we know that 14 of them are heavy smokers with moderate blood cholesterol counts. These numbers here are just from the previous page, and these also. So we've got our observed. We observed 6 patients who were heavy smokers with low blood cholesterol count. We observed 11 patients who were non-smokers with high blood cholesterol counts. So O is observed, E is expected. Okay, so coming along back up here, we now find the expected frequencies. In other words, we find the frequency we would expect, assuming the null hypothesis is true, right? That's what we always do when we have a null hypothesis, or when we have a hypothesis test, we assume the null hypothesis is true, right? Unless we see evidence to suggest otherwise. And again, just like before, we're never proving anything. We're just saying things along the lines of the evidence suggests, right? Our sample data suggest. So we're going to find this E is the expected number. Like, out of these 160 patients, how many would we expect to see who are heavy smokers, low blood cholesterol count? How many would we expect to see if this and this are totally independent? That's what we're going to do. And then we're going to compare these and see if it seems reasonable. So that's what we're looking at. One thing we also have to do is label these cells. And we'll see why in the next page. So I'm just going to write 1, 2, 3, and you should do this too. 4, 5, 6, 7, 8, 9. Because when we figure these numbers out on another page, we're going to have to put these numbers in a location. So if we just label them like this, it just makes it easier. And then what we have to do is figure something out here. So, all right, I'll leave it like this. So here's what we need to do. We want to find the expected frequency of heavy smokers with low blood cholesterol count. So heavy smoker, low blood cholesterol count. We found 6 people here. Out of our 160 patients, 6 of them were heavy smokers with low blood cholesterol count. Now we want to see if these two things really are independent, how many would we expect to see? So that's what we're going to do. So the way we figure this out is we use this. Probability of heavy and low, so heavy smoking, status, low blood cholesterol count, is equal to the probability of heavy times probability of low. And the question is, why is that? Well, here's why. Assuming H naught is true, right? We are assuming H naught is true. That's what we always do. Assuming H naught is true, the events are independent. All right, so since they're independent, think back to the good old days in chapter 4. Probability of A and B. Remember, for this, we've got 3 formulas here, but the easiest one is when they're independent, because then you just multiply these two together. Right, so we're back using information from chapter 4. There's 3 formulas for probability of A and B both happening. The easiest formula was the third one listed on that chapter 4 handout. And when they're independent, we multiply them together. So, since we're assuming the null hypothesis is true, we're assuming these are independent. So the probability of heavy and low, we just multiply these two together. So, to find the probability of a heavy smoker, just think, okay, how many heavy smokers were there? There were, if you look at the row total, 44, right? There were 44 heavy smokers out of 160. 44 of them were heavy smokers. And what about low blood cholesterol count? Well, here's low. There were 6 here, 12 here, 23 here for 41 total, right? So 41 out of 160. So to figure out the probability of a heavy smoker, well, there are 44 out of 160. So the probability of a heavy smoker is 44 out of 160. Multiplied by the probability of low blood cholesterol count. Well, there were 41 of those. Again, out of 160. So you multiply this, 41 out of 160. And I'm going to not simplify this for a reason you'll see in a second. But we know when we multiply fractions, we go straight across. So I multiply straight across with fractions, 44 times 41, 160 times 160, which is just 160 squared. Now I'm going to also do the math here. So if you actually did the calculations, you get about 0.07, roughly 0.0705. So basically 0.07, which means about 7%, right? About 7%. So about 7%, if these were independent, we'd expect about 7% of the patients to have both of these, right? 7% of the patients would be heavy smokers with low blood cholesterol count if these really were independent. So we want to basically figure out 7% of 160, right? But instead of just multiplying 0.07 times 160, I'm going to do it a long way so we can see an actual shortcut, actually. So we're going to do a different way so we can see a shortcut. So I'm going to use this kind of messy thing up here. So if we wanted to find the expected value, there's 160 patients. So how many would we expect to be heavy smokers with low blood cholesterol count? Well, it'd be 7% of that, right? But instead of using 0.07, I'm going to use this. So we basically take this number, 0.07, multiply by 160, right? Like if we knew 10% of these people liked well, this is not even possible. Let's say 10% of them like statistics. We know it's way higher, but just for a number, let's say 10% of these people like statistics. How many would you expect to like statistics out of 160? Well, 10% of 160 is 16, right? So you multiply this by 0.10. That's what we're doing here. 7% of them should be heavy smokers, low blood cholesterol count. So we're going to take 160 multiplied by 0.07, but instead of 0.07, I'm going to use this fraction equivalent because then we'll be able to see a cancellation that'll make life easier. So that's my fractional, I'm going to rewrite that, my fractional equivalent of 0.07, right? 7%. And I multiply this by 160, right? Figuring out 7% of 160. But I do this purposely because now we can see what's going to happen. That 160 will cancel with one of those, and we end up with 44 times 41 over 160, or 11.275. But the important part is to notice how we got this. If you look at this, 44, 41, and 160. Well, 44, looking up here, that's the heavy row. 41 is the low blood cholesterol count column, and 160 is here. So that's summarized in this little table here, which makes it really easy. To find E, it's actually easier than it looks. You just take the row total times the column total and divide by the sample size. So, in other words, if I go back up here. So first I'm going to write what we found. We found that 11.275. So if these are independent, we would expect to see around 11 patients. Now when you write these in here, we don't want to round. So these at the most go to 4 decimal places. So I mean, in reality, may have to round at some point. But for us, they only go to 4 decimal places. So I'm going to write them in here without rounding. So I don't want 11 here. If you put 11, we're going to lose too much information and we're not going to get good numbers. So we're going to put 11.275. So that means if smoking status and blood cholesterol count are independent, we would expect to see around 11 patients here. We only saw 6. So does that mean they're not independent? Well, not necessarily, right? We need to see more. Like, we know there's random variation in here, so it'd be shocking if these were all the same, right? Like, if you flip a coin 20 times, would you be shocked if you didn't get half heads and half tails? No, you wouldn't be, right? Same thing here. There's going to be random variation in here. So we need to figure out the rest of them. So using that formula we just found, let's say I want to figure out this one right here. Well, what I do here, this is, if you look at what we've got, moderate blood cholesterol count, light smoking status. So to find this E, we take the row total, 50, take 50, multiply by the column total, 69. So you take 50 and multiply by 69 and you divide that by 160. So that number would be 50 times 69 divided by 150. All right, so I'm looking for this E. You take the row total, 50, times the column total, 69, divided by 160. And if you do that, let's see, you should get about 21.5625. Okay, I'll do one more. Let's figure out this one. We figure out the expected value here of heavy smokers with high blood cholesterol count. Well, the row total here is 44. Column total is 50. And I always divide by 160. So it'd be 44 times 50 divided by 160. And that should give you 13.75. And if you go through the math on all of those, you should get those numbers listed there. Now, if you're thinking, how am I going to ever remember this? You don't have to. Just kind of let me guide you through this problem. This is the only one we're going to do by hand. And then, so just kind of sit back and make sure you follow so you know where the numbers are coming from. But let me just kind of walk you through this one. And then at the end, after we've seen how it works, I'll show you the shortcut on the calculator. And like I said, that's what everybody does. Nobody does these by hand. And you'll understand why by the time we're done with this. So go ahead and fill these numbers in. And make sure you know where they're coming from. Just so you have a good understanding of what we're doing. So we fill all these numbers in. So we were, let's see, which one's fairly close? Well, this one's pretty close here, right? Like, we observed 15 of these patients who were light smokers with high blood cholesterol count. If they were really independent, we'd expect to see 15.625. So this is pretty close, right? And then some are not so close. So there's some that are close. This one here is not all that close. This is pretty close, not super close. So the question is, what we have to do is figure out, are these close enough? We're supposed to get, 23 here. We're supposed to get about 21 or 22, right? 21.5625. So we should expect to see 21 or 22 patients in this category. We found 23. Well, it's a lot like if you were here's an example. Here's kind of what we're doing. I'm going to put this number here. So let's say you roll a six-sided die. Six-sided die. Now, if you roll this die, let's say 60 times, I'm sure you would not be shocked if you didn't get 10 of everything, right? In fact, I'll go further. What if you're going to go to the store and buy a six-sided die, and let's say you're a gambler and you want to make sure it's a fair die. You want to make sure you're like, I don't want to get a die that's not fair. I want it to land on all six sides with equal frequency. Let's say you go to the counter and you say this, and there's a guy working at the counter says, "Oh, you're not going to believe it. I got the perfect one for you. Just this morning, I rolled this six-sided die 60 times, and look at what happened. I got 10 of each of these." Probably be a little skeptical about that claim, right? So we wouldn't expect to see this, right? We wouldn't expect to get this many just like that. So what if you roll it and you come up with this, right? So the question always is, here's the perfect situation, but you don't really expect to see that because there's variation built in. So if you roll the die 60 times and you get this, is this close enough to the perfect situation for you to say, yeah, it's probably a fair die? So that's kind of the question we're looking at. We know there's going to be random variation built in. We know that we're not going to get our observed numbers are not going to be exactly what the expected numbers say, but are they close enough? That's the question. So suppose this happens. Like maybe this is close enough, but what about this? Now this might be a little strange, right? Like, why is it not rolling at the 3? So in this case, if this happens when you roll the die, you might think, okay, you know what? I don't think this is a fair die. So this is the situation we're in. We know here's the perfect response, but we don't really expect to get it. We expected something kind of close, and the question is, did what we get, is that close enough where we think it probably is? These probably are independent. I mean, we don't expect it exactly the same thing, but it's, is it close enough? This example here is not really a perfect example because this is something that has to do with whether a distribution fits, but it's the same kind of idea. Like when we look at these numbers up here, okay, we really shouldn't expect to get like 6 points. We shouldn't expect this to be necessarily 11 and 13 and 17. We know there's going to be some variation, but the question is, are the observed values close enough to the expected values where we think that these are independent? And we have to use probabilities to figure that out. Okay, so let's look down here a little bit. We've got our formula here. And then this just mentions use the formula here to go on the rest of the table above, which we did. And there's a little note here. In order to test for independence between two statistical variables, which is what we're doing, we're testing for independence between these two variables, we need a sample size large enough that for each cell, the expected number is greater than or equal to 5 for each cell. That's not going to be an issue for us. This is just our meaning that our sample size is large enough. Like where we used to always say n is at least 30, or NP and NQ have to be greater than 5. This is a kind of equivalent of that. So now that we have some numbers filled out, we go to the next page. And this is where you get to really see how fun all this was. So to come up with our sample test statistic, this thing's a lot of work to find. Think how, like, compared to an easy one, I'm going to just write down a really easy one that we used to do. Here was a sample statistic we used at one time. Remember how easy this one was? We just plug in some numbers and calculate. Well, this one is the sum of all of these O minus E squareds over E. We have to sum all those. So what you would have to do, see where we numbered the cells before, 1 through 9. So that's the cells 1 through 9. Here's in each cell, like cell number 1, observed, expected. So we have to go through and list all these. Then we go through this math. So you go observed minus expected. Then you square that. Then you divide it by E, and we get all these numbers. And just for fun, I usually leave a few blank because I know students are like, hey, wait a minute, Kurt. How about you let us do some of these, right? So I left some of them blank so you guys can join in the fun. Here's the formula O minus E squared over E. So you take this O minus E squared divided by E, and you should get these numbers here. So if you went through, you would get these numbers right here. And then you can see that we've got the formula up here. So the chi-square is the sum of all of these. So we take all these numbers and add them up to get our test statistic chi-square. And if you do add all those numbers up, you get 18.708 roughly. I mean, that's good enough. So we don't have to go further out here. But basically, to find this test statistic, it is a ton of work. We finally come up with all these numbers and we add them up. And then we go from there. So to see where we go from there, once we have our test statistic. So this is kind of like our z-score, right? We're using when we use the standard norm, we'd have a z-score. Students T had a t-score. With chi-square, this is our chi-square score. And we're not going to develop an intuition for this like we did with z-score. Like if I tell you a data point has a z-score of 5, if you've been paying attention at all, you should know that's a really, really rare data point. A z-score of 5 is really unusual. We're not going to develop that intuition with chi-square because we don't see it as often, and we're really, I mean, the class is almost over, so we're just, chi-square is not used as often, and we're just not going to talk about it as much either in class. So we will see, though, that this is a really high number for a chi-square. It's a really unusual number. So for our example, we got chi-square equals 18.708, rounded to 3 decimal places. And then to develop some kind of idea about what this means, here's what we can do. If you look at observed minus expected, think about if we expected to get 11 people and we got 11 people, then observed minus expected would be 0, right? So we would add up a 0. And we're going to sum, so we're adding these up. So if observed and expected are really close all the time in all those cells, or are the same all the time, then we're going to get really tiny numbers here, right? Like if they're the same, we get a 0. So we're adding each of these chi-squared, so we'd get a really small number, right? If the observed number, if we saw 7 of those clients and we expected to see 7 of them, then we go 7 minus 7 is 0. And if it was happening like that a lot, where these were either the same or really close, we would add up a bunch of tiny numbers and we get a really small chi-square. All right, so this is what this is saying here. When the observed frequency and the expected frequency are very close, they're real close, O minus C squared is close to 0. So chi-square will be small. As the difference between O and E, the observed and expected increases, chi-square increases. So if smoking status and blood cholesterol count are independent, the observed frequencies should be close to the expected frequencies. Because remember, we were finding these expected frequencies based on those two variables being independent, right? We found this based on them being independent. So if the number that we found was real, or the number we expected based on them being independent was close to the number we actually found, then these are going to be close to each other, and we're going to get a small chi-square. So smoking status and blood cholesterol count are independent. The observed frequencies should be close to the expected frequencies, and chi-square should be small. So determine how large chi-square can be before we reject the null hypothesis of independence. We need the p-value, same as before, right? There's a lot of carryover to each of these sections. The p-value, the sample test statistic, and the chi-square distribution. And of course, the p-value depends on the number of degrees of freedom, just like you did with students T. So we got a formula for us to figure out the degrees of freedom for a test of independence. Remember what we're doing. It's a hypothesis test, and it's a test of independence. We're testing two variables and seeing if they are independent. And the variables in this case are just blood cholesterol count and smoking status. So the way we find it for degrees of freedom here, it has that familiar like n-1 shape, but now there's two variables. There's the row variable and the column variable. So for degrees of freedom for test of independence, there'll always be a table. So there's always going to be two variables. Each of them have this n-1 look. So you have r-1 times c-1, row -1, column -1. So in our case, so we've got number of rows, number of columns. Remember, our table was a 3x3 table. We had 3 rows and 3 columns. So in our case, degrees of freedom will be 3 minus 1 times 3 minus 1, because we had 3 rows and 3 columns. 3 minus 1, 3 minus 1. Which, of course, is 2 times 2, right? Which is 4 degrees of freedom. 3 minus 1 is 2, 3 minus 1 is 2, so we have 2 times 2, or 4 degrees of freedom. So to test the hypothesis that smoking status and blood cholesterol count are independent at the alpha equals 0.05 level of significance, or in other words, the 5% level of significance, we find the p-value shown below. Now, this p-value, there's nothing new there. That p-value is p-values that we already know about. In other words, it can be interpreted as the area under the curve, and it can be also interpreted as the probability we would get the sample we got if the null hypothesis is really true. So we've got 4 degrees of freedom, so we want to graph that graph we already did. Chi-square, PDF, X, and 4, which you may even, is probably still on your graphing calculator. We want to draw that one here. So just think of the first picture you drew and take a second and draw that on there. So here's my drawing. Again, it's drawn by hand, so it's not going to be perfect. But you will notice one thing. Our chi-square is 18.708. And if you look along this number line here for 18.708, it's way over here. Like, basically this, in theory, this chi-square goes over here, right? In theory, it goes forever. Remember, what's the area underneath this curve? Exactly 1. And we are way over here at 18.708. So we're like right, I don't know, about right there. right? There's about 18.708. So the p-value is the area under that curve to the right, which is going to be, up until this time, this is going to be the smallest p-value that we've seen, I believe. It's going to be a really small p-value. It's there's just not much left. The area under the curve is 1 altogether. We have this little tiny slice. If you look at your graphing calculator, you'll see there's just not much left there. It turns out for test of independence, for these tests of independence, we always use a right-tailed test. So that makes it kind of easy. It's going to be right-tailed test all the time. And it'll be easier anyway because our calculator, like I said, will do the work for us. But it's just something we need to know for test of independence is a right-tailed test. And then to recall here, the p-value is the probability of getting us the sample results or more extreme results when the null hypothesis is actually true. And in this case, it's also the area under the curve to the right. It's a right-tailed test, so it's always going to be to the right of our test statistic. So you can see there is just not much left there. Our p-value is really tiny, which means we've got a really strong evidence against the null hypothesis. So to find the p-value, we could use a table. Now, nobody really does, but you could. So there is a table 7 on page A25 if you really want to use a chi-square table. With the TI-8384, we can do it a lot quicker. We can get better details too. So we press the distribution key. We've seen this before. And we want this chi-square CDF. And here's the format for the chi-square CDF. We need the lower bound, upper bound, degrees of freedom. It's going to be very, very similar to what we've always done. Now for the upper bound though, here's the difference. 10 won't be enough usually, but 100 will. So remember, if you think of the graph that we made went to 20, and there's nothing left at 20. So if you go all the way to 100, you might as well be infinity, right? And because remember, in theory, that number line that we drew with a graph, let me move this back over here. In theory, this goes to 100, right? Or goes to infinity, goes on forever. But you can see it's already so close to the curve you can't even distinguish it. So if I go to a chi-square of 100, it's just like infinity. So I just use 100 because it's easy to remember because we did it before with normal CDF and students T. We always use 10, just use 100. You really don't need it. You could use probably 30 or probably even 25 would work, but 100 is easy to remember. And it's always right-tailed, so it's always going to be our number, comma 100, because it's always right-tailed. So the way we do this on the calculator is we go p-value equals the probability that chi-square is greater than or equal to 18.708. We don't use normal CDF. We don't use TCDF. We use chi-square CDF. Chi-square CDF. Lower bound is 18.708. Upper bound is 100. Degrees of freedom 4. Remember, this can be any number, probably 25 or more. 100 is just easy to remember. And when you do this on your calculator, you get a really small number. Remember, chi-square CDF is just from the distribution key. It's where all the normal CDF, TCDF, it's where all those are. And then when this comes up, just punch 18.708, 104 with the commas in there, and we get our new p-value, or p-value for this problem, which is really small. And remember what you don't want to do on your calculator. So I sort of skipped a step here. I skipped a step. So the calculator showed something like this, but remember, we don't want that. It's not standard notation. This is American calculator notation. So scientific notation would be okay, but this is probably better for us just to write it as a decimal. But we definitely don't want this. It's not standard, right? So if you put this times 10 to the negative 4, that would be standard. That's scientific notation, but we definitely want to avoid calculator notation. So here's our number, very small. It's a really tiny p-value. And then we come to our conclusion. And this is going to be very similar from what we've seen before. So since the p-value is less than the level of significance, way less, right, in this case, 0.0009 is less than 0.05, we reject the null hypothesis, right? So nothing new there. We look at the p-value, right? We compare it to the level of significance alpha, and the p-value is way less, and as long as it's less, we reject. And then I'm going to show you the wording, and if you look in the back, the wording changes a little for this section. You don't have to change it. The wording we used before works just fine, but I'm going to write it a little bit differently this time just so you can see how they do it in the book. So here's what we've got. You notice this is exactly the same as before at the 5% level of significance. That's how we have started every single conclusion to a hypothesis test. Now, we still, if you notice, the book is still going to word most of the conclusions in terms of H1. They just changed the wording a little. Here they say there is sufficient evidence to conclude. I'm just going to look at this one. There is sufficient evidence to conclude. Do you guys see that that is just like saying the sample data or evidence suggest? It's just like that. It's just a different way of saying the exact same thing. So I'm just writing it this way because for whatever reason in chapter 10, the author starts talking in this way. And I don't know, maybe it's just to see, there's different ways to say these same things. So you can use the old wording if you want. You could just say the sample data suggest or something like that. Or you can say there's sufficient evidence to conclude. And now we're just going to write H1, right? We rejected the null hypothesis. We rejected the null hypothesis. So we are going with the alternate hypothesis. So if you look over here, we're basically saying H1. Here's H1, smoking status and blood cholesterol count are not independent. Isn't that just H1 right there? That right there is H1. So that part's the same as before. We mention alpha, and then we say there is sufficient evidence to conclude H1. Now you could also say, when you say not independent, if you wanted to, you could say, or are dependent. Sometimes the wording's a little weird because we got all these like negatives here. Not independent. You could just say smoking status and blood cholesterol count are dependent instead of saying not independent. Totally up to you. But the main part is just to see that the wording's a little different, but we're basically saying the same thing. So whatever kind of wording you want to use is fine. Both of them work. There's sufficient evidence to conclude. Or you can use our old language where we said the data seem to suggest or the data don't suggest, however you want to do it. But what I want to do is I want to show you the other wording. If this had happened, which it didn't, but I want you to show the wording if the p-value is greater than alpha, so we fail to reject. Because with this language, I basically can rewrite this same thing with just add 2 letters to change it. Okay, so let me show you what I mean. Okay, so if you look at this one, you are going to see that there is just one difference between these two. And the difference is, right here we said sufficient. Right here we say insufficient. So I guess this wording maybe makes it a little easier. So in this case, we rejected H naught, so we're saying there's sufficient evidence to go with H1. Here, had we failed to reject, now we didn't, this is not true in the case of our problem, but I just wanted to see the wording, right? I'm just concentrating on the wording here, that's all. So if we had failed to reject, if we had done that, the only difference is I changed sufficient to insufficient. That is the only change here. That's it, because this says sufficient evidence to go with H1. This says insufficient evidence to go with H1. Right here we rejected H naught, so sufficient evidence to go with H1. Here we didn't reject H naught, insufficient evidence to go with H1. And again, it's only because our book typically phrases everything, all the conclusions, in terms of H1. So it's just, the wording you can use pretty much on all of these problems. Whether you reject, you'd use something like this. Fail to reject, use something like this. But the question is always about independence. So, all right, so you have seen now the hard way to do this. And you can see why nobody really does it that way, because it would take so long to do those calculations. Because a lot of those calculations that were on the handout, I already did them. If we were doing them from scratch, it would just take a long time for every single problem. So, before I show you the easy way, let me just mention one more thing. So the little note here. So what we concluded was that smoking status, right? We concluded smoking status and blood cholesterol count are not independent. That's what we concluded. But we are not able to make conclusions about individual categories such as light smoker and dependence or independence to blood cholesterol count. Okay, so it's just the whole thing, smoking status and blood cholesterol count. We can't break down into individual categories. So, okay, that's just a little note. And now I'll show you how to do this on the calculator. Also mention this comes up in homework problem number 8. They asked something about this. So to do this on the calculator, we're going to use a matrix. Now, I don't know why, but every time I hear the word matrix, I think of Keanu Reeves. Anybody else? Or just me? Could be just me. I don't know. But we're going to use a matrix on the calculator. And so I'll show you how to do this. So to do test of independence on the TA83 or 84, we use a matrix. So see above the X inverse key, it says matrix. So we go second matrix. And then you'll see some of them listed here. And we just have to go over to edit. So we'll move over to edit. And I'm just going to select matrix A. And it comes up and it's showing the size. Right now it's a 1 by 1. Well, we need to make it the size of our contingency table, which is a 3 by 3. So I just hit 3, enter, 3, enter. And then I put the numbers in this matrix the same way they were originally in our table. So you go back over to where on the first page of the handout and we fill the numbers. So we have a 6. And you just hit enter and you keep punching the numbers in. I'm just copying the ones right off the table. And let's see, a couple more. So we've got our numbers from the contingency table are now in our matrix. So then I'm just following the directions there on the handout. So it says enter the observed values into matrix A. So those are our observed values. So they're all set. And then it says press stat. So go to the stat button. So press stat. Then go over to tests. Go over to the tests. And then we want to choose the chi-square test. And it's down here a ways. It may even be faster to scroll up. But eventually we'll get to this chi-square test. So we hit enter. And then it tells you where it's going to look for the observed values in matrix A. It says expected values in matrix B. We don't have a matrix B. That's okay. What it's telling you is it's going to put the expected values in matrix B. So all those values that we calculated by hand and took quite a bit of time, it's going to do those immediately and store them in matrix B. And then so we can just go either calculate or draw. I'm just going to go calculate. If you hit draw, it will show you the curve and the shaded area for the p-value. So I'll go to calculate, and it gives us everything. It gives us our chi-square test statistic, gives us our p-value, gives us our degrees of freedom, and then we would just have to be able to look at the p-value and make the conclusions from there. So this is how you'll do the homework problems and the test questions. As I mentioned in the video, nobody really does these by hand other than just to learn how they work. And then so once you do one or two by hand like we did in class, all the homework questions, just do them just like this. And then just to show you, if I go back to that matrix, so I go back to the matrix menu, so I go second matrix, and now look, there's a matrix B. So I could go down to B and then go over to edit and select it, but I'm going to show you what else you can do just to see it. If I go down to B, matrix B, and hit enter, and then hit enter here, it'll show up. And the dots here mean that if I scroll to the right, it'll show the rest of them. And those are all those values that we went through and calculated by hand, and the calculator does them immediately. So that is how you do the chi-square test on the TI 83 or 84. So hopefully that made sense. So try them out, try the homework problems, and remember, we're really just going to do it this way, right? This is what we're going to do. So you don't have to do them by hand, just do the homework problems using this technique right here, like I just showed on the calculator. And if you have any questions, of course, let me know.